And it's official. We're now week 10. Welcome back, everyone. So our goal for week 10 is just to continue working through chapter 7. Our big one will be finishing off for sure 7.2. We may or may not finish off 7.3. We'll see where we end up when we're on Wednesday. The other major announcement is, like we mentioned just a moment ago, we finished exam 2 on week 8, and now we already have exam 3 kind of on the horizon. That's just evenly spaced out 4 weeks apart for the exams. That means you can expect the same exact things that happened before exam 2 are going to happen down here. Once I get to Friday of the week we're on currently, week 10, I'm going to put down the official information for what's going to be included on exam 3. It looks like it's going to be section 6.3, 7.1, 7.2 for sure. 7.3 is kind of on the fence. We'll see where we end up on that one. I'll put in the review problems, 2 different versions, just like before. And don't forget, we discussed this on the end of Wednesday's class. The math department has a calculator policy, just excludes the TID4 graphing calculator, but also has a note card policy, which says I can't print formulas on exams, except for the final exam. That's the only exception, unfortunately. So this document, even though it's an early draft, this is a good one to look into, have it pulled out, use it maybe for your homework, especially for studying on exam 3, as a reminder of things that need to be memorized for the purpose of the 3rd exam. Once I get to Friday of week 10, so the end here, I'll have the finalized draft of this as well as the rest of the materials. But any questions with the announcements at the moment, folks? Or any questions whatsoever, really? Okay, well, let's start then. Chapter 7 is pretty intense, like we already found out in section 7.1. Lots of identities we have to use. We're not really looking into geometric trigonometry as much like we did in chapter 5, chapter 6 with the graphing, and even the inverse functions. We were using a lot of geometry on the unit circle to do all those evaluations. Chapter 7 is all about analytic trigonometry, using formulas to our benefit to simplify and compute things. And so just for a warm-up before we go into section 7.2, let's do another 7.1 problem. That's this little warm-up document right here. Or we'll just prove another identity just to get our brains in the right kind of mode and just to review some of those ideas back from section 7.1. It says to prove an identity, but really this could have just said simplify, delete all that, and it's the same kind of problem. Those are the 2 major problem types we did in section 7.1, but really the idea is it's kind of the same problem. If it's an identity problem, you at least know where you're going. You know what one side is supposed to equal at the very end. And this one's really similar to a homework problem, except I switched the denominator from a tangent to a cotangent. There's a lot of major strategies. One thing we might look for when we go to prove these identities is there an identity that could help us? Usually we're thinking Pythagorean identities, and section 7.2 and beyond, there'll be other identities on the table to help us out. But I don't see anything too major here, and trying to force in a Pythagorean identity is probably just going to make the algebra more complex than it needs to be. So a second thought might be something along the lines of convert everything into terms of sines and cosines and use algebra. So we want to isolate the more complicated side so we can simplify it down. That'll be the left-hand side. And really, these are identities in the same sense, but these are the ones that we should always have in the back of our mind from chapter 5. The fact that a secant x is just a 1 over cosine x. Cosecant x is just a 1 over sine x. And likewise, a cotangent is just a cosine x divided by sine x. So this is our work so far. The identity gets uglier sometimes before it gets better, especially for converting everything into sines and cosines. And now at this stage, we just have to try something. What could that something be? It's not always easy to see, but sometimes if you just simplify a complex fraction, things have a way to work out. This is where the second advice comes in. Sometimes a lot of these problems are just more about being familiar with algebra and the cleanest way to try to reduce something or simplify something. If you have a fraction, as we do, Yet there's fractions in the numerator of your fraction and in the denominator of your fraction. This is overall called a complex fraction. And there's a really slick algebraic technique to just simplify this in one go. You look into the least common denominator. The least common denominator in this problem is going to be cosine x times sine x. So if we multiply like this, it's going to get even worse, but things simplify. Multiply by cosine x over cosine x, then sine x over sine x. Then we can distribute into the numerator, distribute into the denominator, and overall it has this effect. I'm going to need more space than that. Let me try again. Cosine x sine x multiplies here into that numerator. Let's keep that same color coding. Cosine x sine x. Divide by cosine x. It's a lot of copying, but for the sake of showing just exactly what's happening, this is not a bad step to write in. Plus, sine x was that denominator. But the numerator, when we're multiplying fractions, we can multiply numerators into numerators. It puts a cosine x, sine x into this numerator. Now we're multiplying the denominators into the denominators, but then we're using the distributive law at the same time. This becomes 1 times cosine x, sine x. Then we add plus in the middle, so just maintain that plus like we did in the numerator. Cosine x is here. Then it gets multiplied by that whole expression, so times cosine x sine x. Divide by sine x. Now my hand is already tired and my class just started, but that's all right. It's good to write this out just to show exactly how it goes. The fun part's the cancellation. These common denominators designed to just kill off all your denominators. So cosine cancels, here sines cancel, and down here sines cancel as well. We're left with a lot of stuff overall. Sine x plus cosine x in the numerator, cosine times sine plus cosine squared in the denominator. So here are the survivors, sine x plus cosine x over cosine x sine x plus cosine squared x. So it's been simplified. We have to know when to stop, but then the next strategy is you're trying to get to secant x. That's the right-hand side we're trying to link things up to. Right-hand side is a secant x. Next good idea is, as you try to solve this further, keep in mind there's a goal, there's an end result we're trying to get to, and the secant is 1 over cosine. So I'm working one side at a time, but we skip to the right-hand side just to see what we're going for. If the secant is 1 over cosine, that means our major goal is to get a 1 right up here, and nothing but a cosine down in the denominator. There's still one last thing we can do. The denominator is complex, but the next big idea that comes up a lot with these identities or simplified problems is you can simplify things just by factoring. There's a greatest common factor in the denominator of cosine and cosine in both of those terms. So if you factored that out, a cosine x, I'll just highlight that without the power, you'll get sine x plus cosine x. Factor out cosine x. That leaves behind sine x plus cosine x. And that's exactly what we'd like to see, because now sine x plus cosine x is a cancellation with that entire group in the denominator, leaving a 1. We have the 1 we're trying to link up with on the right-hand side, cosine x in the denominator. So this stage, you could take another step, but if you took that other step, you're right where you need to be. This is exactly the right-hand side. So that's a way to do this kind of problem. This is how we did something similar to these while we were in class. Any questions at all, folks, with this overall approach? Oh, didn't need to highlight it all. So that's a way to do things. Looks like this one didn't involve any Pythagorean identities. You know, honestly, that would be the first thing I would look for whenever I see this. Is there a sine squared, a cosine squared, a tangent squared, or secant squared in your problem? If there is, particularly the last exercise in this homework set, consider using those identities and simplify. And sometimes what could have been a pretty long problem like this one here can resolve a lot faster than you might think. Well, let's try this out one more time. There's more than one way to do these kind of problems. So sometimes if you had a moment of inspiration, you might have thought of a totally different way to do this. We mentioned that a couple times with some of these problems. Some of the problems are so wild and wide open that there could be something like a half a dozen different correct solutions I see when I go to grade them. This one's not as wide open, but there is a cool way to solve it. You could write this as secant x plus cosecant x, 1 plus cotangent x in a whole different kind of way. Forgot to call it left-hand side, so let's just throw that in there in the left. Secant x, if we go to sines and cosines, is 1 over cosine x like before. Cosecant is 1 over sine x. Cotangent is cosine x over sine x. And factoring, it helped us out on the last approach that we took. Factoring is, a really good idea sometimes if you can just get it to work just right. We want a 1 over cosine x. Let's see what would happen if we factor out 1 over cosine x from the enumerator this time. You know what? That works. You can do that. You would get something like this. 1 over cosine x factors out of the numerator, leaves behind. Factoring is just a kind of division. When I factored cosine from this denominator, I divide cosine here, leaving sine, divide cosine here, leaving cosine power 1. So if I factor out 1 over cosine, this cancels, leaving a 1. I double check it with the distributive law. Cosine x times 1 is back to the cosine x we had before. Factors out of this term, it just looks really weird. This will be plus cosine x over sine x if you factored out cosine x from that term. How does it work? Well, if you multiply this way, 1 over cosine x times cosine over sine cancels the cosine, and you just get a sine x back, 1 over sine x. If you notice that one weird step, then you have 1 plus cosine x over sine x in the denominator at the same exact time. And this is the fast approach. That now just completely cancels as one big group. So you have 1 over cosine x as the leftover, and that's back to the right-hand side. That's secant x, which is the right-hand side. So sometimes clever factoring is really all you need with some of these problems. But to be totally honest, this is not something I would have thought about as my own. This is only because, well, we've done similar problems already. This is a pretty similar homework problem. And I helped a couple students with this, just got my brain thinking about it. Sometimes these problems take a lot of different attempts. Sometimes you'll have to try different strategies, different things. It really is just one kind of weird puzzle. There's no one formula that says this is exactly how every single identity is going to go. So creativity, persistence is really kind of the major things that you need to get through them. Well, that's looks like about a 12-minute warm up. Any questions about either approach on solving these? Okay, if you want to come back to this document, I'm going to post it under somewhere over here around 7.1 because that content is a little bit more similar. And it's a good warm up for a number of reasons. Section 7.2 has more identities. We'll be doing several more identity proofs in section 7.2 and 7.3. So we'll be keeping these ideas refreshed as we go through chapter 7. So let's jump back to section 7.2 then. Here's where we left off on Wednesday. It's kind of a rough screen to come back to, so let's let our eyes adjust. We have the addition formulas, or sometimes called the sum and difference formulas, or identities. There's really 6 of them altogether. There's a pair for sine, a pair for cosine, and a pair for tangent, and there's a striking pattern as well. Sine gives us a sine cosine, the cosine sine pattern. We just have to be mindful of the signs. Cosine gives us a cosine cosine sine sine pattern. This one's a little bit more dangerous because the plus here converts to a minus, so there's an opposing direction, and the minus goes to plus. Likewise, tangent, the one we're going to practice next, has the same pattern. Notice how the alpha betas just line up in kind of a pleasing way to the eye. There's a pattern there, and that makes everything a little bit easier to memorize. If you do tangent alpha plus beta, then the thing to keep in mind is the plus sign is maintained across the numerator, and then you switch to a minus in the denominator. You add up your tangents in the numerator, you take 1 minus the product of the tangents in the denominator. If it gets switched up, say there's a minus, and let me hit that with green. That's going to bug me otherwise. If there's a minus, then the sign is maintained in the numerator again, and then we just switch what the sign is going into the denominator. Same exact pattern, it's just a difference of tangents, and 1 plus the product of tangents. On some of the problems, we'll know what alpha and beta are. In other problems, we'll have to come up with the alpha beta, kind of like this cosine problem. We had to decompose pi over 12 in this way, pi over 3 minus pi over 4. There's more than one way to do that even. So if you thought of doing it as, say, maybe a 6 pi minus a 2 pi, or excuse me, you have to get 1 pi over 12. I had to think a little bit harder on that. Oftentimes there's more than one way to do that, but not 6 pi minus a 4 pi. Make sure the difference is 1 to get the 1 in the numerator. So we'll try out the tangent ones next. Here's the next problem to take a look into. 23 pi twelfths. That's kind of random, kind of like cosine pi over 12 is random. This is 15 degrees. And now we're doing a multiple of 15 degrees on 23 pi twelfths. But we can calculate that, and we can compute it exactly. Let me zoom out again, just so we can have the identities above. The first thing we need is, what is alpha, what is beta? So let's begin working on the inside, 23 pi twelfths. We want to just break this up as some amounts, either added or subtracted. Here we went for a subtraction. That's just because we had 1 pi. There's 23 pi's. Then, addition between the two might be easier to go with. I'd probably try 23 pi. Let me try again. I'd probably try 20 pi plus 3 pi. It's not guaranteed to work. You might have to find a slightly different arrangement. But my goal is, I want to be able to reduce 20 pi twelfths and 3 pi twelfths. So next step is to divide 12 into both. 20 pi twelfths plus 3 pi twelfths. And we want these to reduce in a way that we get an angle much like the ones we've seen before. Maybe a pi over 6, a pi over 4, pi over 3, or a pi over 2, or any multiples of any of those key angles from quadrant 1 of the unit circle. And it looks like we're in good shape with this, because if we divide by 4 into this fraction, we'll get 5 pi over 3. Divided by 3 into numerator, denominator to that fraction, and we get pi over 4. That's going to be our alpha and beta. So we can break down tangent into a sum formula. Let's scroll down just a bit so that we can see what all the work is going to look into like. This is going to be tangent of 5 pi over 3 plus pi over 4. That's good because now we're expressing tangent into angles we can work with. Next step is we need the identity. And because these are things we have to memorize for the exams, really good idea here is just write it down on paper. It goes like this: tangent alpha plus beta, thinking in terms of how the identity was written out, becomes tangent of something plus tangent of something else. So this is just the format of the identity. I'm sensing I need a little more space on this one. Divide by 1 minus, now the product of tangents, tangent of something times tangent of something else. So if we have plus here, we maintain the sign in the numerator, but add the tangents, go to the opposite side in the denominator, and last thing to do is just drop in what is alpha, what is beta. So this is the alpha, this is the beta. 5 pi over 3 will go here and here. The pi over 4 goes here. Oh, looks like I made a mistake on this. Let me try again with my identity. I had it written like this and it kind of looked nice at first, but that's supposed to be the sum of the tangents, right? So plus tangent of something. And the product of the tangents, it should have been times tangent of something down here as well. Okay, my correction is, don't forget to actually write down tangent. It's a function, so we need to say what the function is, then put in the inputs. Let's pause right here in case you're making any corrections. Any questions at the moment? Okay, we've got the identity down. Now import alpha and beta. 5 pi over 3 goes here and here. Pi over 4 goes into the remaining positions. And if we were doing something with sine and cosine and an addition formula or a difference formula, it would have been the same idea. 4 positions to put in the 2 different angles. Next thing we have to do is actually calculate this. This is an evaluation problem, so the end answer is one number. We have to say what tangent 5 pi over 3 is, tangent pi over 4. But then it just becomes a review problem. This work regresses all the way back to section 5.3. There's a different time back in 5.3. There's just the unit circle and angles like pi over 4 and 5 pi over 3. 5 pi over 3, the mnemonic here is pi over 3 is here, 2 pi over 3 is here, 4 pi over 3 is way over here, and this one is 5 pi over 3. Let's calculate these both so we just have them ready and we can drop them in where we see these values. First tangent pi over 4 is not so bad. That one equals 1 because it's sine divided by cosine, and both values are square root 2 divided by 2. Tangent 5 pi over 3 probably takes just a little bit more work. Let's work that one out carefully. Tangent 5 pi over 3 is going to be the sine value in the numerator. That's in quadrant 3, so it's a negative root 3 over 2. Divide by the cosine value in the denominator. That one is, just as it looks, 1/2. The divide by 2's cancel, and it's just a negative root 3. So now we know exactly what goes here. That's negative root 3. We know exactly what goes here. That's just a 1. And we make 4 substitutions, same substitutions in the denominator. So now it's equal to negative root 3 plus 1 divide by 1 minus negative root 3. Oh, meant to color code that. Let's just slap it with a highlighter. Tangent pi over 4 is a 1, so times 1. That means it's just about there. It turns into altogether negative root 3 plus 1. Let's actually switch the order of that. Just looks a little bit nicer. I'm going to call this 1 minus root 3. We could have left it negative root 3 plus 1 for the same value. Denominator is now 1 plus root 3. And here's where it becomes a choose your own adventure style problem. I want to emphasize, especially for exams, I would stop right here. In an exam setting, there's no real benefit going any further on this problem. You've got the right value. It's in a certain simplified form. So let's say here, this is a very acceptable answer. And let's say even more, it's a great stopping point. on an exam. It just has one small issue. The denominator is not rationalized. So if you were to check this answer in the back of the book, it's probably not going to look like that. They're going to simplify this even further by removing the irrational number square root 3 from the denominator itself. Let's take that strategy just for the sake of gives us a little breather before we go into the next identities, and just in case you might want to do that in your homework. Just a reminder, you don't have to. Probably not even a good strategy on the exam setting. This is perfectly acceptable right where it stands. But for the sake of the homework, this is what you would do if you kept on going. It's 1 minus root 3 divided by 1 plus root 3. We're now digging deep into pre-calculus 1, college algebra material, maybe even intermediate algebra material. We want to rationalize the denominator by multiplying by its conjugate. The conjugate of 1 plus the root of 3 is 1 minus the square root of 3. And this has a nice feature. The numerator can get complicated when we FOIL out the numerator, but the denominator is automatically guaranteed to simplify in a huge way using the idea that a plus b, that's 1 plus root 3, times a minus b, that's 1 minus root 3. This is a difference of squares. It reduces to a squared minus b squared immediately. And that's in the way we kill the root 3 from the denominator. It turns into, let's work the denominator first. 1 times 1 gives us 1. If we didn't use this formula at all, it doesn't matter. It's still fast to FOIL. Here to here is negative root 3. Then root 3 times 1 is positive root 3. The middle cancels. That's why there's just 2 terms up here. And positive root 3 times negative root 3 is negative root 3 squared. That's just a minus 3. A root times the same root just kills off the square root. FOIL out in the numerator, and we'll get 1 minus root 3. Now distribute the negative root 3. It's going to be minus root 3 again. The negative root 3 times negative root 3 is positive root 3 times root 3. That's positive 3 altogether. So this is simplified in a certain sense, but this is more simplified. So my goal is to convince you of that. We just have to continue to simplify it. In the numerator, it is 4 minus 2 root 3. We have to combine the roots. Those cancel in the denominator, and it's just a negative 2. Divide negative 2 to the numerator, and you get negative 2 plus root 3. So the sign flips when you divide here, the 2's cancel. And because we maintained a long track of equalities, the big summary here is that tangent 23 pi 12ths is negative 2 plus root 3. So now we know. So if we ever had to calculate that exactly, if society melts down and we can't use calculators any longer, we can still do the exact value on 23 pi 12ths for tangent, sine, cosine, and all the other functions as well. But any last questions at all, folks? Simplifying this one. Okay, the big idea was just going from here, tangent alpha plus beta becomes this through the addition formula. We'll practice all the other addition formulas a little bit more with the next examples. And each time we have to use one, I'll always put it down on paper. These first problems we did, part A and part B, they're kind of intense. There's lots to calculate. We even went back to section 5.3 to do these evaluations. But not all of them are this hard. Some of them go just extremely fast. We just have to know what the identity is and how to use it. So that's what's going on with example 2 next. It says use the addition formulas for sine and cosine to simplify the expression. We'll do a couple versions. First, we have to decide which addition formula we're using. This becomes pattern recognition now. It's kind of like the same problem, but it's backwards. It goes sine, cosine, cosine, sine. So that's an addition formula for the sine function. That means, let's write down what the identity would be. If there's a minus, this is going to be sine alpha minus beta. So we need the difference formula going this way. Pattern for sine alpha minus beta goes like this. Sine and then cosine. Maintain the middle sign minus and then cosine and then sine. Barely got that last parenthesis in there. So maintain the alpha beta in this pattern here. Alpha beta, alpha beta. So that's the identity we're going to use. Double check it fits this format. We have the negative sign in the middle with sine cosine, then cosine sine. That just means alpha for this problem is 3 phi, and beta is phi. The whole problem then turns into sine alpha minus beta, using that addition formula. Plug in what alpha and beta are. Double check. It's exactly 3 phi here and exactly phi here, or else the identity wouldn't work. But this one's all set. This is now just sine 3 phi minus phi. This turns into, we still have to simplify it all the way down, means combine like terms, but that's not the worst thing we've done all day today. This is just sine 2 phi. And it's done right at that step. There wasn't really a lot to show on paper, but really the big idea was there's 6 addition formulas, some are difference identities. We had to see that this one connects with that one specifically. So that's the pattern recognition part of the problem. The more you memorize these identities, the more that you work with them, the more you just practice writing them down on paper, the easier it gets. We'll try it out to part B next, but any questions on part A? Yeah.
Where does the cosine here? How's that here?
So the question was, are you referring to how this cosine gets removed from the equation?
Yeah.
This one and this one?
Yeah.
Well, that was really just the whole identity itself. The identity for the original sine alpha plus beta, much similar for like cosine itself, is that if you use a cosine identity, the sines are just eliminated. And likewise for the sine identities, both of them, cosine itself, it gets eliminated. It just turns into one sine function altogether. That's kind of what makes this identity so powerful in a certain sense, that you can take something really complicated on the right-hand side and reduce it to one trig function, even though there's 4 factors on the right-hand side, all with different angles. The only one we proved was this one, and it was through some addition formula, or excuse me, distance formula, and lots of algebra in the middle to get there. The same thing happened. It turns into something complicated. But if you simplify this down, you can arrange for all your cosines and sines on one side and just one cosine function on the right-hand side. Same thing happens when you go to prove these ones down below. But does that help out with what's going on with that one? Awesome. So they're really strange identities, especially with that question that you just asked. Cosine is part of it, but if you use it going from the complicated side to the simplified side, cosine is just gone. We'll see the same thing happen in part B as well. But any other questions so far before we try out that part B? Okay, let's think again. Which identity is this one? It's not the one for tangent because tangent involves fractions like this one. They get ugly fast, so it's a dead giveaway. When you see sines and cosines, there's really 4 good choices. If on the terms you get sine cosine, it's telling you it's the sum difference identity for the sine function. If you go cosine cosine, sine sine, it's the other half of the addition formulas. So first thing I would write down is cosine alpha beta. Notice I left the sine blank here. This one's really tricky. I like the sum formulas for sine and tangent because they maintain what you see on the inside with what you see on the opposite side. But the one for cosine is a lot different. If you see a negative here, let me highlight that one and this one. A negative here gives you the opposite sign on the inside. So what should go here is actually plus. To me, that's the trickiest thing about this. They are in opposing directions for the addition formula for cosine, whereas sine and tangent, they go in the same direction for those signs you see here to here. The rest of the pattern is not so bad. Cosine goes cosine, cosine. If it's plus, it changes direction to minus, and then it goes sine, sine. In fact, this is the one that we proved on the very top of the notes. The middle sign is negative. Angles go alpha, beta. So alpha, beta, alpha, and beta. So we just have to double check. Do we really have that same pattern? This would be the alpha. Same alpha here. This would be the beta, pi over 3, pi over 3. And yeah, if you write in pi over 6, pi over 3, this entire right-hand side is this right-hand side here. So we've got a match. The hardest thing is finding the right identity because there's 4 good choices. Alex says, is it ever sine alpha, sine beta, cosine alpha, cosine beta? Yes, that could happen. So if that were to happen, it could have been a problem that goes kind of like this. Sine pi over 6, sine pi over 3. I think this would be a fair question for the homework, but maybe not as much for an actual real exam question, because then it feels like we're just trying to disguise the identity. So for something like you said, for sine alpha, sine beta, cosine alpha, cosine beta, it could have been written this way, plus cosine pi over 6, cosine pi over 3. So now all we have to do is just rewrite it into this form, and then we could use the identity. If it was, say, like this, then that's okay, but it would mean we're using a totally different identity here. It would have been minus with the plus in the middle if it was in that form. As far as secant goes, secant is not too bad, because if that one ever comes up, you can say secant alpha plus beta is 1 over cosine alpha plus beta. But then once you get that far, oh, beta came along for the ride on that one. Once you get that far, you can just rewrite this as 1 over cosine alpha cosine beta minus cosine alpha cosine beta. So if any other reciprocal function comes up, you just use this idea, use the identity purely in the denominator. Does that make sense with those 2 questions there? Yeah, absolutely. This one would be really tricky because it feels like we're putting things out of order on purpose. So I probably wouldn't like this so much for an exam question. This one would be a kind of a tricky exam question as well, because the ones we majorly focus on look like in this format. But both questions, they could be things that do come up in homework. So they'd be things to watch out and try to spot. But then as far as part B goes, we did the hard work once we identified which is the right identity to use on it. And then the rest of the problem is just use the identity. It's now equal to cosine alpha plus beta. Oh, that was supposed to be green. There we go. We'll plug in what our alpha and beta are. This is now cosine pi over 6 plus pi over 3. And this one keeps on going as opposed to part A. Part A involved an algebraic expression in the variable phi, 2 times phi, so it just stops right there. But this one, if you know what the angles are, we have to keep on going further and evaluate them. So this is now equal to, let's add pi over 6 and pi over 3 together. It equals cosine pi over 6 plus 2 pi over 6 to get the least common denominator. All I did was multiply that fraction by 2 over 2. Now it's equal to cosine 3 pi over 6. Now it reduces further. Cosine 3 pi over 6 is just cosine pi over 2. But cosine pi over 2 is exactly 0. And what a strange problem. This looks like it's something really kind of built up, but you're literally looking at 0 once you work it through the addition formula for cosine. It's a good idea to highlight how the negative here went to positive. That's an easy thing to get mixed up for the cosine version. But any questions at the moment, folks? Finishing off this one? Okay, we have one more to take a look into before we try something slightly different. But so far, all we've really been doing in examples 1, 2 is just practicing these identities, the same 6 ones we studied at the top of the notes. So here's our next practice run. Involving the tangent identity, lots going on with this one, but it has the same pattern. We have a difference of tangents, a product of tangents. The identity for this one goes tangent alpha minus beta. The sign in the numerator flips to the denominator, but it's the sign that goes here when we state the identity. This is equal to tangent alpha minus tangent beta divided by 1 minus tangent alpha times tangent beta. Oh, excuse me, almost there, plus tangent beta. So the signs are maintained at the numerator, and then they flip in the denominator. That's exactly what we're looking at here. This is our alpha. This is our beta. It matches the format that we see on the right-hand side here. So we could just plug it into this version of the identity and crank it out. So this turns into tangent alpha minus beta. The work on the right-hand side was just to check, do we have the right format of the identity? Did something go wrong that could break the algebra? But if everything is in the right pattern, all we need to do is simplify this. We'll plug in the angles next. It's tangent of 11 pi over 21 minus 4 pi over 21. That's not so bad. These already have the least common denominator, so slightly nicer than part B in that sense. This turns into tangent of 7 pi over 21. Then it reduces, so we can keep on going further. This is tangent of pi over 3. We can compute that exactly. Pi over 3 puts us up here, quadrant 1. Versus the sine value right over here, that's root 3 over 2. Divide by the cosine value, which is down here, that's the 1/2. Divisions by 2 cancel, and we just get square root of 3. So it looks monstrously complicated, just comes down to that. The problem ends, the algebra ends right precisely at that step. Well, we did it, folks. That's a pretty good tour of the addition formula so far. We'll practice them in a little bit more, just looking into trigonometric identities next. Any questions whatsoever, looking into any versions, part A, B, or C here? Okay, addition formulas are kind of the key to all the major identities in trigonometry beyond the Pythagorean identities. In fact, once you have the addition formulas, you can finally give a really cool analytical way to say, why do we have these relationships, a sine function and then something called a cosine function? In what way is cosine co to the sine function? We never really resolved that in a strong, satisfying way. You can somewhat do this in chapter 6 if you look at different graphs. But I think to me, this is a little bit more convincing. We can prove right here, right now, why this function here is co to the sine function. It's just a phase shift. Its sine moved right by exactly pi over 2. Recall from chapter 6, this part right here says the phase shift is positive pi over 2. The cosine graph is just the sine graph moved right by that precise distance. And we can prove that right here and now, finally. We're only going to prove one. There's 6 cofunction identities altogether. But you know, every single one of these goes in the same way. We have to combine some of Andrew's questions where we never stated an addition formula or some difference formula for any of these 3 functions. But if we go to the top of the notes, take the reciprocal of all of these identities, we have those actual functions. those identities. So these are not identities I'm going to ask you to memorize for the exam. This is more for the sake of completeness. Here are all of the cofunction identities, and we'll just prove one of them. The sine theta is cosine theta minus pi over 2. It is just like in section 7.1. We are proving a legitimate identity. So what I would do here is start with the most complicated side. That's the right-hand side, cosine theta minus pi over 2. Our next idea is to try to simplify that. Well, there's only one cosine function. I don't see how it simplifies. You might express it in terms of sines and cosines, but that's done. Here's cosine. And the next thing is try to fit an identity to it. We've got an identity ready to go. We can say that cosine alpha minus beta is cosine alpha, cosine beta. Watch the sign change. This always trips me up personally. Plus, oh, that always feels kind of harmful to the brain to have a mismatch of directions. Sine alpha, sine beta. Our alpha and beta are these two. So we can just throw that into that difference formula for cosine just immediately and see what happens. This will turn into cosine alpha minus beta. So it's cosine theta sine pi over 2. Then the minus here flips to a positive. Then it's two sine functions. Yeah, question first.
Cosine.
Oh, sorry about that. Thanks for spotting it. I should have had my identity right there just to help me out, but now we got that correction. Thanks again for spotting that in class. It should go cosine, cosine, then sine, sine. So now we've got our cosines in line. It's next sine. Theta comes in. Sine again. Pi over 2 comes in. And good fix, because if we put a sign here, we're not going to get the identity to come out right to any way, shape, or form. We would have just been stuck until we found that mistake. But now that we're here, here's the beauty of this problem. Cosine pi over 2 is 0, so this whole term is just gone. This is cosine theta times just 0 altogether, plus sine theta times, well, sine at pi over 2 is exactly 1, and multiplying by 1 doesn't change the value. So we get a cancellation right here. That's just gone. 1 times sine theta is sine theta. And that's the left-hand side. So that's how this one goes. If we go the same for cosine, the same for tangent. This is algebraically messy because you have to take the reciprocal of all your identities, but it would go the same exact way. Just a little bit more writing, or they're dealing with fractions now. We'll look into one more identity before we close out these notes officially, coming back on Wednesday, which leads into all the other identities we're going to see in section 7.3. But any questions or comments at the moment, folks, with where we're ending at today?
I do have a question.
Yeah, go ahead.
So in the identities, the pi over 2 is on the left side of the minus sign, but in the problem we just did, it's on the right-hand side.
Oh, good call. So one of the things I did here, just to make it a little bit faster to track, was I took this. This is how the book writes them, and I'm honestly not a huge fan, but you can take cosine pi over 2 minus theta, go cosine, factoring out a negative, and now it's theta minus pi over 2. I flip the signs and change the order, but then you go all the way back to 7.1. Let's take a tour here. 7.1 has a resolution to just this situation where it tells us about the, hold your breath on it. Where did they go? Oh, even in odd identities, finally. So cosine is special. That negative sign that we just factored out can be full on deleted. It's just gone. So a negative there gives you cosine of the thing inside. that's the thing inside I'm really thinking about. So this turns into cosine theta minus pi over 2. Oh, let me bring that back. So that's the identity that I snuck into the problem here when I wrote it down in this way. This is just a little bit easier to prove in this form. I liked it in this form because it directly relates to the phase shift too, tying back to chapter 6 concept. Other questions at the moment? Okay, same idea works for all of these. You can flip theta, make it come first. Just use your right to even odd identity to force that in. I didn't put this on the list of identities to memorize. They're good identities, but my exam can't involve every single identity. And so it's going to be a little bit more straightforward. I'm not going to give you the negative angles like you've worked out in some of the homework problems. But occasionally, like we've seen, they're useful, so we'll use them as necessary. Well, I think I've added material for folks. When we come back next time, we'll prove this identity, which turns out to be one of the 3 major ones that starts off the next section notes. The hint is you just use another addition formula and it proves those next identities. Well, have a great night, folks. If you have any other questions while you're working on any of these problems, don't hesitate to write. I'll be happy to help out. Next class, we'll finish off 7.2 pretty quickly and then move into the next section. Well, I'll see you all next time. Yep, thanks for the questions and the corrections you spotted. Take care.